Hey class, today we're going to do Chapter 8, Section 3, and this is about bonding theories. We're going to focus on today the VSEPR theory. Everything that we've been learning so far, I've been teaching you how to draw electron dot structures. But one thing to know about those structures is that they fail to reflect the three-dimensional shapes that molecules have in the real world. For example, methane, which is CH4, we draw with a carbon in the middle, bonded to 4 hydrogen. Now this structure is very flat and it's only two-dimensional, which doesn't reflect how things look like in the real world. So in reality, methane molecules are actually three-dimensional, and if you look over here on the right, they tend to have more of a pyramid shape. We're going to notice the hydrogens in methane are at the 4 corners, and it actually forms a geometric shape looking like a tetrahedron or that pyramid. When this occurs, those angles that are formed between hydrogen bonding to carbon is actually going to form an angle known as the tetrahedral angle, which is about 109.5 degrees. So if we look at the ball and stick model, it tends to look like this structure down here. So what does the VSEPR theory stand for and what does it mean? The VSEPR theory that we're going to learn about states that the repulsion between electron pairs are going to cause certain shapes to occur because those electron pairs are going to adjust themselves to stay as far apart as possible. And the reason for this is because of something you guys actually learned at freshman year of science, like charges want to repel. If you have an electron pair that's a negative charge next to another electron pair that is a negative charge, they're not going to want to be by each other because like charges, again, repel. So what do we actually use the VSEPR theory for? We can actually predict how these electron pairs are going to react, and it allows us to determine the three-dimensional shape of molecules. And one thing to know is that VSEPR actually stands for valence shell electron pair repulsion theory. In other words, how do these valence electrons repel one another? There are very common molecular shapes that can be created based on how these electron pairs repel each other. We have linear molecules, bent, even tetrahedral like we saw with methane, and then more complex ones like octahedral or square planar. So how do we actually determine which of those shapes it's going to form? So first we're going to answer these questions, and that's what's going to help us determine that. If there is no central atom, which means if you only have 2 atoms there, the shape is automatically going to be linear. For example, if I have hydrogen bonded to fluorine, notice that there are only 2 atoms, and so therefore there's nothing for it to bend around, and so it has to stay a straight line. However, if there is a central atom, there are 2 things you're going to have to determine. The first thing you're going to have to determine is the number of bonding groups that come off the central atom. In other words, how many things is that central atom bonded to? I do give a hint, double and triple bonds actually only count as a single bonding group. For example, HCN. If we look at our central atom, it only has 2 bonding groups because it's bonded to this hydrogen and then it's bonded to the nitrogen. This triple bond, again, only counts as 1 bonding group because it's only bonding 1 atom. The second thing we have to understand is looking at our number of lone pairs on that central atom. So if we look at carbon, I don't see any lone dots of electrons, so there are no lone pairs. And then we're going to take a look at our class handout to determine what molecular geometry it needs to be. So what does your handout look like? It's going to look something like this. And there are 3 main columns we're going to look at when we do this. First, we are determining the electron geometry here. So we're going to look up here in this column. And then in order to do that, we need to look at the bonding groups and our lone pair. So we're going to look at this column right here. Oops, did not mean to do that. And then this lone pair column right over here. So let's look back at methane again as our example. How did we know methane actually forms a tetrahedral? Well, when we look at methane, it actually has 4 bonding electrons on it. We see that methane bonds 1, 2, 3, 4 hydrogen off of it. So it's 4 bonding groups. But if we look at the central atom, there are no lone pairs. So there are no lone set of electrons on carbon. And so when we actually use the VSEPR sheet, I'm going to see I have 4 bonding, but 0 lone pairs, and my molecular geometry is actually going to be tetrahedral. Notice that next to it, it says that my bond angle is going to be about 109.5, and if we look at this example, it shows us that our angle is going to be 109.5. Another type of shape that can formed would be trigonal pyramidal. And a common thing that does this is ammonia, which has the formula of NH3. If we look at ammonia, it's bonded to 3 hydrogen atoms, and it has a lone pair on it. And these unshared, also known as lone pairs, are going to be very important in predicting the shapes as well, which is why we have to look out for them. When we look at this, we're going to notice that there are 3 pairs that are bonded. So we have a bond here with hydrogen, another bond with this one, and then another bond over here. That's where we get our 3 bonds. And then it says we have 1 pair of lone pair of electrons. And so this is our lone pair of electrons down here. So 3 bonding and 1 lone. If we actually look at this and we have 3, again, bonding, 1 lone, it tends to form trigonal or trigonal pyramidal. So that's the shape that we see with ammonia. And then also notice it says our bond angle is less than 109.5. So if I actually look at this, you're going to see that its bond angle is about 107. Why is this the case? The reason for this is no bonding atom is vying for those unshared pair of electrons on ammonia, and therefore those electrons are held closer to nitrogen than any of those ones that are bonding hydrogen. The unshared pair is going to strongly repel the ones that are being bonded, and it'll push those ones slightly more together than it would in a tetrahedral. So we say that the angle is about 107, or the handout will say less than 109 degrees. Another example of a shape is bent. A good example of a bent molecule is water. When we look at water, water has 2 bonding groups. So here it's bonding a hydrogen, and here it's bonding a hydrogen, and so that's where it's getting its 2 bonding groups. It also states it has 2 unshared, or we call those lone pairs. So for example, up here we have a lone pair because it's not bonding anything, and over here we have a lone pair, again, not bonding anything. So we end up getting 2 bonding, 2 lone. And if we look at our handout, 2 bonding and 2 lone actually gives us the shape of bent. And this tells me that my bond angle is going to be less than 109.5. So we're going to notice when we actually look at that our 2 unshared pairs are going to repel my bonding pairs in a way in which makes my angle about 105. So again, this is less than 109 degrees. The reason we put 2 less than symbols is because if we just had 1, that's about 107 degrees, but if we put 2, it's going to be even smaller than that, which is around 105. The last one we're going to kind of look at is linear. We tend to see a linear shape between the carbon and the oxygens that are bonding in carbon dioxide. When we look at this, it says that there are 2 bonding electron groups. So if we look at this structure down here, carbon is bonding 1, 2 things. That's where it gets its 2 electron groups. And then it has no unshared or lone pairs. If we look at carbon, there's no lone pair of electrons that's not bonding something. So we tend to have 2 bonding and no lone pairs. So up here, if we have 2, again I did not mean to. If we look up here, we have 2 bonding, but 0 lone pairs, we're going to see my shape is linear, which automatically makes it 180. Anything that is linear is always going to be 180 degrees. And we can actually look at that. The double bond is going to be about 108 degrees apart. And so we say carbon dioxide is linear. So what causes the valence electron pairs to stay far apart as possible? Again, it's because they have like charges. So essentially their negative charges are going to repel one another. If you don't like the way I explained it, that's all I really got for you, and that's what our book says, so just make sure that you guys get that down. We are going to look at 4 examples of how do we tell what shape things are. So first thing we're going to do is we have to be able to draw the structures correctly. So here xenon gives me 8, fluorine gives me 7 apiece, but I got 2, so this gives me about 14, which actually gives me about 22 electrons that I'm working with. Xenon's going to be in the middle, flanked by fluorine on either side. Here I used 4, that gives me about 18 electrons left over. I'm going to make my fluorine happy. And there I used about 12 electrons, which actually gives me 6 left over. Anytime you make the outside happy and you have some left over, remember we're going to put them on xenon. So I'm going to put a pair here, a pair here, and a pair here. Keep them in pairs, please. You do not split them apart. When we look at this, now that we have it drawn, we can say, okay, we're going to look at our central atom, which is xenon, and we're going to look, how many things is bonded off of it? I have 1, 2 fluorine bonding, so off of it. So I have 2 bonding. Then we're going to look at xenon and see how many lone pairs we have. I have 1, 2, 3 pairs of lone pairs. Then we're going to go to our chart and find where does it say 2 bonding and 3 lone. So here's my bonding. This one says 2 and 0, 2 and 1, 2 and 2. Here we got 2 bonding, 3 lone pairs. If I go over here to my molecular geometry, we're going to see that it is linear, which is about 180 degrees. So we're going to say that this structure right here is linear for our shape. Let's look at example B. Here, sulfur donates 6, fluorine donates 7, and 7 times 6 is about 48. If I can do math, which actually gets, is that 48? I know, I'm going to sound stupid when I record this video, but if you ever need help with multiplying, it's okay that you do that, because thank goodness I did, because that's actually 42. We're actually going to add 6 to that, which that's where I'm getting my 48, is totally added together. Off that sulfur, we're going to bond all 6 of those fluorine. So here, when we bond all 6 of those fluorines, we actually made it 6 bonds. Each of those have 2 electrons, so we're actually going to subtract 12. It's going to get me down to 36. And then from there, you're just going to make sure that all of your fluorine are happy. When you make all your fluorine happy, you're going to notice that you end up using all 36 electrons that are given to you. From there, we can figure out the shape by then asking how many lone pairs and how many bonding pairs off our central. So our central is sulfur. How many things are bonded off sulfur? We have 6. So here we have 6 bonding. And then we're going to look at sulfur again. How many lone pairs do I have? And we have 0 lone. Again, we're going to go back to our chart. We're going to see where's my 6 bonding. So here's 6 bonding, 0 lone pairs, and my shape is actually octahedral. So sulfur hexafluoride is actually an octahedral. Over here, we're going to look at this example. We get 2 electrons from hydrogen because there's 2 of them, 4 from carbon, and 6 from oxygen, which actually gives me about 12. Carbon ends up being our central atom, and we are going to bond it to our hydrogen and oxygen. We end up using 6. That gives me 6 left over. But then we want to make sure that everybody's happy, so we end up taking this pair and getting rid of it and making a double bond. Now we can ask ourselves how many bonding and how many lone. If we look at carbon, it's only bonding 3 things. So we actually have 3 bonding, 1 hydrogen, an oxygen, and a hydrogen. Again, notice this double bond counts as a single bonding group because it's only bonding 1 thing. Then we're going to look at the central atom. Notice that carbon doesn't have any lone pairs on it, so it has 0 lone. So we're going to look at what is 3 bonding and 0 lone. Okay, here's 3 and 0. So our structure is trigonal or trigonal planar with an angle of about 120. So trigonal planar is its shape that we end up getting. And last but not least, we have HF, which I kind of already showed you this one. Hydrogen gives us 1, fluorine gives us 7, which gives me 8 electrons that I'm working with. Notice here, when I make this structure, there is no central atom. Since there is no central atom, you do not have to use this chart at all. You just have to notice there's no central atom, which automatically makes it linear. And linear structures are always about 180 degrees. And that's it for today's lesson. If you have any questions, please ask, and I hope you guys have a great day.